today is entitled Offensive Development and Post-Exploitation Tradecraft in an EDR World. So who am I? Well, my name's Dominic Chell. I work for a company over in the UK called MDSec, mainly focusing on offensive security. Day to day, my role is relatively hands-on. So I spend most of my time leading and executing red team operations for our clients. You can find me on Twitter under the unimaginative handle of @DomChell. I try and also contribute back to the red team community. So I'm quite active on Twitter, on the MDSec blog. So you can find some of my research and some of the blogs posts on there. So before I dive into the talk, I'm going to start off with a little story. So let's say, maybe this is atypical for many kind of red teams. So maybe you've spent days concocting the perfect phish. You've engaged the user. You finally got them to open that payload that you've weaponized and prepped to bypass EDR, and then you get your beacon check-in. So what's next? How do you operate? Well, maybe you want to do some basic situational awareness. So maybe you check your privileges with things like who am I? Maybe you check that you're on the right network, on the right environment with things like ipconfig. Maybe you probe the endpoint a little bit, trying to discover some documents that might be of interest. And then once you're happy that you're on the right endpoint and you've finished with it, maybe you want to kind of move laterally. So maybe you use something like Bloodhound to gather information about the Active Directory and look for potential opportunities for lateral movement. And then finally, you discover another system in the network where you've got admin rights. So maybe you want to move laterally, so you upload a DLL to the remote system, to the remote host, and then you stage it with something like run DLL 32 or equivalent. And then suddenly the beacon's gone, it stops checking in. You probably start to question yourself. Maybe the user went to a meeting, maybe they finished for the day. You start to kind of wonder what's happened, up until the client drops you that message saying, oh, sorry, the blue team detected you and they've isolated your endpoint. So at that point, you may have spent days or weeks, and then suddenly you need to start over. And I'm sure this situation has happened to almost all red teamers, and it can be quite frustrating. So let's take a little look at what the blue team actually saw in this scenario, and perhaps we can look at some potential approaches to improve our tradecraft. Okay, so firstly, they've got an EDR that captures process creation events. So they can see PowerShell spawning ipconfig. They can see us running who am I. They might be able to see us using various lol bins. This, of course, doesn't blend in very well and will no doubt raise the threat profile of the endpoint, particularly if the user has never run any of these before. The EDR is also catching ETW events. So they've seen all of our .NET tradecraft. Maybe they're even like baselining the processes that will load the CLR. So the fact that we've got W32TM as our spawn to process and it's loading the .NET runtime, this might in itself be an indicator. But then we've also got things like the sharp hound assembly names sitting, it being communicated back through ETW events. So this is probably not ideal and probably stands out. And if not, it probably should. So perhaps some elements of that story resonated with you. And that is the crux of my talk today. It's really that the defenses and the environments are becoming more mature, and blue teams really have got that home field advantage. As a red teamer, there's a lot of different things that we actually need to deal with. And at least most of the client environments that we kind of red team against, and they'll have things like command line logging, PowerShell logging, they'll have sandboxes, EDRs, EDPs, application whitelisting, AMSI, ETW. All these kind of technologies are basically creating a minefield of defenses that we as a red teamer need to navigate through. And because of this, actually, in order to be successful, what we find is that as a red team, we have a growing investment in our operations. And the last thing that we want to do really is have entire campaigns, entire techniques, or entire tools burned very quickly through incident response. So in this talk, I plan to basically look at this problem in greater detail. So I'll start off by examining some of the techniques that are used by blue teams to actually detect post-exploitation tradecraft. I'll look at, once we've kind of looked at those, I will look at ways to actually go and understand how they're catching us, and then potential ways to evade these detections. We don't just want to actually evade them, but we also want to integrate these evasions into all of our tools. So every tool that we run, we want to basically bootstrap these techniques into them. In addition to that, I'll also cover a few different approaches that we can leverage to really better protect all our tools and intellectual property in scenarios where we do end up being detected, and also try and increase that time from detection to kind of ejection, really. So I'm going to start off initially looking at kind of historic tradecraft, and traditional tradecraft is typically involved running OS commands on the endpoint. So this might include things like leveraging lol bins to perform certain actions. So for example, maybe we want to actually download a file. So to do that, you might use something like bits admin as a means to accomplish it. Now, of course, this is not a recommended approach for a mature environment. And that's basically because if the blue team is capturing process creation events, they'll trivially be able to monitor and see everything that we're doing. So one of the methodologies that I want to propose is, can we actually abstract ourselves entirely from this concept? Can we actually only ever operate on an endpoint in code? Now, there have been some steps taken. I do think the answer is yes, and there have been some steps taken to move in this direction. So we've seen the introduction of features such as execute assembly in Cobalt Strike, which basically allows us to execute .NET tools in unmanaged processes. We've also more recently seen the introduction of things like beacon object files, which basically provide an interface to execute C code inside a process. So I'm going to start off looking at some different approaches for actually detecting .NET tradecraft. And the reason we're starting to see this really is mainly because red teams moved over to .NET following the introduction of PowerShell defenses. So this, of course, led to much more focus from the blue teams in techniques to detect .NET post-exploitation tradecraft. And one of these techniques, which is documented in this great blog post by the guys from Countercept F Secure, basically shows how we can use event tracing for Windows to integrate it into our EDRs and into our EDR telemetry, our blue team telemetry, to actually go on and receive CLR runtime traces through an ETW consumer. This is really powerful because it can provide deep visibility of all the assembly names, namespaces, class names, method names that are being run in the .NET runtime, even when we're using like an unmanaged surrogate, so using something like execute assembly. So the consequence of this really is the blue teams now have at their disposal tools like Silky ETW by FuzzySec, which can basically allow them to monitor all .NET executions, even in unmanaged processes, and actually signature them. So signature all the function calls and method names and class names and things that are being run, looking for known .NET tools. So that gives the blue team great insights to .NET post-exploitation. So what are some approaches we can actually leverage to kind of evade or get around these detections? So the most obvious one and the most trivial one to avoid at least signature detection is just to obfuscate the assemblies. So renaming the namespaces, the class names, the method names, all this kind of stuff can actually help us slip past some of the signature-based detections that some of the blue team tools might be using. This is quite simple to do, and we can take advantage of some of the open source obfuscators, things like ConfuserX, and these will actually help us to change up our binary before we run it. So as you can see here, we've got a very simple example of how a safety cats assembly might look in the disassembler after it's been run through something like ConfuserX. And as you can see, it's much less signature friendly. There's fewer strings than in the original unprotected binary. So that's great. We can now obfuscate all our binaries. Another thing that we might want to do, aside from obfuscation, is potentially just try and stop the .NET assembly actually sending any ETW events entirely. So we can actually do this, and the reason for this is mainly because the ETW events are sent from userland, and they're sent from a process that we have already got code execution inside. And because inside .NET we've got access to the full process memory, we can actually just go on and simply patch the functions that are relevant for sending ETW events. So for example, inside NTDLL, there's the ETW event write function. And if we patch this to just return, we can basically remove that ability or visibility of the ETW events for the blue team. How that might look if we've got a patch process. So if we dived into it with something like Process Hacker, we might see something like this, where we haven't actually got any events it being reported up to the consumer. So what other kind of tools, what other kind of techniques and things are available or at the team's disposal for detecting our .NET Tradecraft? Well, version 4.8 of .NET Framework introduced AMSI, and I'm sure many of you are familiar with this. And basically, it will be called, AMSI will be triggered anytime an assembly is loaded through something like assembly.load. It will basically allow the AV engine to go on and scan those bytes of memory. This, of course, isn't a huge problem. As I already mentioned, .NET exposes the full process memory, so you can leverage one of the traditional AMSI bypasses, something like the AMSI scan buffer patch, which Cobalt Strike actually offers through the AMSI disable malleable profile config option. You can actually leverage this to just go on and patch AMSI. Now, that in itself is fine from a red team perspective, but inadvertently you might also be creating an indicator of compromise, because what we've started to see, and there is a blog post referenced at the bottom by the guys again from F-Secure Countercept, we started to see blue teams actually using memory scanners to hunt for modifications of code sections, so basically looking for patches to AMSI DLL and memory. So as a red teamer, you might want to kind of leverage this technique cautiously, and once you have leveraged it, go on and restore the original values inside the AMSI DLL to basically limit the window for detection. So aside from that, how about actual detecting actual tools? So one of the most common CLR harnesses that are used is the execute assembly method inside Cobalt Strike. So I've mentioned this a couple of times. The way it basically works is it will inject the CLR into an unmanaged surrogate process. And this is one of the probably the most widely used tools for achieving .NET execution. Now, there's a few kind of techniques that the blue teams can employ to actually go on and detect tools like execute assembly. So the first one is basically down to the fork and run behavior. So as I mentioned before, the way it works is it will spawn a new process, inject the CLR inside it. Now, that kind of behavior from the blue team perspective, you might want to actually look for suspicious process creations, anomalous parent-child relationships. So it's potential to detect it that way. Additionally, there's no kind of ETW bypasses built inside execute assembly. So if you have got an ETW consumer, you can collect all these events and look for the signatures and things that I kind of mentioned before. Aside from that, we might also, if we're monitoring for module loads, is maintain like a baseline of processes that are actually loading the CLR, so that every time execute assembly runs, it will cause the CLR to be loaded into this surrogate process, and several modules will actually be loaded inside the process. So things like CLR JIT.dll, CLR.dll, and whatnot. So if we're maintaining a baseline of processes that will legitimately load the CLR, and the operator is not blending in with their spawn to, then potentially we might have an indicator of some .NET post-exploitation behavior happening. And then finally, I also spent some time actually digging into how execute assembly works. And what I discovered were there are a number of specific IOCs in its behavior. So because of this fork and run kind of methodology that it uses, that basically means it's going to require process injection. So within Cobalt Strike, you can actually customize, the process injection techniques are malleable, so you can customize them. So you can control things like the page protections. So for example, you can basically say a page should start read write execute, or can be read write execute, or a page can end up read execute. And this is done through the start RWX and use RWX malleable profile options. Basically, what that means is that our .NET binary will always be sitting inside a page that is allocated read write execute or read execute in the surrogate process. So if as a blue teamer we start to hunt for firstly processes that are loading the CLR, and secondly, once we found those processes, pages inside them that are read write execute or read execute and have a .NET P binary inside of them, then we can actually not only detect when a .NET post-exploitation, but we can also actually carve out the .NET PE. Now, you might think, well, what about things like assembly.load when it happens legitimately inside the CLR? Well, actually, just because of the way the CLR works, the pages with things like assembly.load are never actually executable because they're jitted. So at least from my testing, this becomes a very specific behavior through execute assembly, and becomes a way to actually detect it. So I can show you a demo of this. So I'm just going to try and screen share. Let's try this. Can everybody see my video? Yes, excellent. Okay, I have videoed all these because I was a little bit nervous about doing them over a live stream. But basically, I've got Cobalt Strike running with a beacon up here, and then I've got a very simple. I'm just showing you the code for a very simple .NET binary, .NET tool that we're going to run through execute assembly on the endpoint. Now, all this tool does, as you can see, is just sit there printing something to the console. Basically, I'm just going to run this. So we're going to run it on this endpoint through execute assembly. Okay. And you'll see all it does is just print sleeping. The reason I've done this is just so we can leave the process running and kind of show you how to kind of pull this out. So inside the malleable profile, the spawn to is set to background task host.exe, which we can see is now spawned in process hacker. So I wrote a tool called Sniper, which will basically scan all the processes on an endpoint. I'll just pause this here. It will scan all the processes on an endpoint, and it will look for the ones that are using that have CLR.dll loaded, and then when it finds those processes, it will then walk through virtually allocated memory, looking for pages with read, write, execute, or read, execute page permissions. And if it finds them, it will then look at the start of those pages, looking for PE binary headers. Okay, and what you can see here is that the Sniper tool has basically found a process called background task host. It's shown that it's loaded the CLR.dll, and then about midway through on this command prompt, it says found PE binary in region, and let's give the base address, and then it says carving PE from memory. So I'll let this run through, just this bit that I've highlighted here. So if we take a look at that actual page in memory, so I'm just going to use Process Hacker to actually find the right page. So just here. So I'll just pause this here. So I've used Process Hacker basically just to show you what the memory looks like. And at the page that it's identified, we can see we've actually got a PE binary, which is has been carved using the Sniper tool, has actually been carved and written to disk. So we can take a look at that actual PE. So you can see here it writes it to a file called out.exe. So if I run this, now obviously I wouldn't recommend running any arbitrary PE you've just carved from memory on in a real kind of blue team investigation, but given I know what it is, it's relatively safe to do, we can see it's actually the original .NET PE binary that we ran through Cobalt Strike with execute assembly. So now we've got a great way to not only detect execute assembly, but also recover the binaries that are being run through Cobalt Strike. Okay. So hopefully you can see the slides again now. So as a if we're a red teamer and we're looking to actually improve our tradecraft with execute assembly, there's a couple of things that we might want to consider. So firstly, we might want to actually try and select a surrogate process that will legitimately be loading the CLR, and this can help us avoid those CLR load baselines. Secondly, we might actually want to stomp the .NET PE headers inside our .NET binary because they're not actually even used. And then we might want to actually go on and reset the page permissions. So maybe we want to reset them to read write so that we actually blend in with the behavior of things like assembly.load, because as I mentioned before, the page never actually needs to be execute, never needs to actually have the execute permission because the CLR will JIT it. So how can we actually go and find suitable surrogate processes? Well, I did this using sysmon. Sysmon event ID 7 will basically show module loads. So we can use sysmon offensively to actually go on and look for processes that are loading the CLR. So a good example of this is background task host, which you can see is loading the CLR.dll. So this might potentially be a good option to use in our spawn 2 configuration within Cobalt Strike. Secondly, if we want to actually stomp the PE headers, again, what we can do is bootstrap something like this into our .NET code. So we would bootstrap this into every .NET binary that we run. And this will basically just firstly recover the base address of the process. It will then overwrite the first 132 bytes of memory from the base address such that it basically nukes the PE header, and then we would go on and reset those pay permissions to be read-write. And this might actually help us avoid detection from memory scanners that are looking for .NET binaries in memory. So I guess, like, to summarize, like, what I'm trying to show or trying to say, and we've covered a few different evasions there, to actually go on and maximize our .NET Tradecraft, we might want to, we might need to bypass AMSI, we might need to bypass ETW, we might need to stomp PE headers, we might need to reset page permissions, we might need to obfuscate our binaries. So a lot of different things that we might need to do to try and keep our .NET post-exploitation tradecraft invisible. If we're trying to actually manually apply these to every .NET assembly that we run, it's probably not going to be feasible. So I guess, like, fundamentally what I'm trying to show is that because we want to bootstrap all our code and dynamically build all our code, then in an automated way, this is very much in the DevOps territory. So I started to kind of look at this problem, and it seemed to me that the best solution was to actually try and integrate all my tools inside a CI/CD pipeline, and that would hopefully allow me to weaponize them on every build. And before I dive into my approach and the tools that I kind of created to do this, there has been some work in this space already, which you should probably recognize. So firstly, there was a really interesting blog post from Adam called Building, Modifying and Packing with Azure DevOps. And secondly, there was also some another blog post on the MD-Set blog called Offensive Development with GitHub Actions, which again, uses this CI/CD pipeline approach to automatically build and obfuscate all your tools. But for me, rather than trying to use something like one of the existing pipelines, something like GitHub Actions or Azure DevOps, the approach that I took was basically to try and build my own custom one. And the reason for this was mainly because it would give me greater flexibility, and it would also allow me to easily integrate other third-party tools. So to do this, I basically ended up building a .NET Core Web API project. The reason I chose .NET Core was because it was, it's platform agnostic. You can use it in Docker, and it's also got a really cool compiler built inside it called Roslyn, which basically acts, at least in my project, as the core engine for building and manipulating all my tools. And then finally, I was also actually able to integrate my tool, this pipeline, with things like Donut. So that basically then gave me the ability, using Donut's .NET Core bindings, to actually turn any of my projects or any of my code into shellcode. So that basically means that I can also use them within any kind of custom loaders that I might have. So the project that I created, the pipeline that I created, was basically a tool called Covert Toolsmith, and I'm hoping to actually release this at some point in the near future. So there's three kind of core components to it. So firstly, there's a loader, which ends up getting run on the target endpoint using a CLR harness, so something like execute assembly or any kind of custom CLR harness that you might have. And this is basically what is used to bootstrap all the code. So you can use it for adding, like, bootstrapping an ETW bypass, or keying your binary before it actually gets run. And I'll talk a little bit in more detail around how that works later. Then there's also the projects. So these are basically all the kind of .NET tools, whether those are public tools or whether they're your own kind of in-house custom tools. So things like a Ghost Pack, or maybe any kind of artifact loaders and things that we might want to drop to disk or execute in memory. And then the final component is the actual engine. So this is basically the .NET Core Web API that will receive requests for projects. It will then go on and consume the project source code, bootstrap them, compile them, protect those binaries, and then return the compiled and encrypted project back to the user, back to the loader. The loader, there is like a lot of flexibility in this. I've kind of tried to build it such that you could use it in different ways because it's all done through API requests. But basically, the loader is optional. So you can, if you wanted to say, just recover an obfuscated or keyed copy of like Rubus or a copy of whatever project, you could do that, and then you could run it on an endpoint, or you could use it with a CLR harness, however you wanted to approach it, really. So the architecture looks a little bit like this, and this is like an example of one way you might be able to use it. So I also tried to make it like C2 agnostic, because it is just a web API. So as long as there's some way to script inside your C2, then you could basically take advantage of it, because we use multiple C2s, and we've got our own implant and things as well. So but if you're using it with something like Cobalt Strike, I basically wrote like an aggressor script that will firstly make a request to the Covert Toolsmith API, saying I want this tool, whether that tool is Safety Cats, Rubus, or whatever project that you want. Then Covert Toolsmith will build that tool, modify it, obfuscate it, bootstrap it as needed, return that tool to the actual the C2 client, and then the C2 client can basically run that however you want. It can you deliver it to the endpoint and use like a custom CLR harness, or use execute assembly, whatever kind of harness you want to actually use to execute it. And I'll show you a little example in a few slides' time, so you can kind of get an idea of how it actually works. And then in the end, the actual compiled and protected tool is run on the actual endpoint in memory. And it might, say, for example, if it's keyed to that endpoint, it can brute force its own decryption key and run it in memory there. It can apply the ETW bypasses and things, anything that's been bootstrapped onto it. In order to kind of build tools, there is a little bit of configuration that needs to happen in advance. Basically, what we need to do is tell Rosalind the resources that are required to actually go on and compile that tool. So every project has got a little JSON configuration file that is associated with it, and it basically says, in this example, when you compile this project, use all these references to basically build it, and then each of these config files are serialized and stored in like a small SQLite database that is within the Docker container, and these are basically then accessed on every compilation request for that project. So I'll show you again a little demo of how we can run a .NET tool using this pipeline. So hopefully everybody can see that. I can see there's like there's a few questions. I will kind of address these at the end. So firstly, I'm just going to reset the parent process, basically just so we can see what I'm going to show you how this works. In that, if we were using something like execute assembly, it would spawn a new process where the child process, whatever's defined in our spawn to, is associated with the parent of Beacon, because we're not doing any PPID spoofing. So I'm just going to show you this initially to show you how it might work with execute assembly. So I'm going to run a binary, and we can see we've run, you can see on the left-hand side, we've run Rubus, and on let's just backtrack a second. On the right-hand side, in Side Process Hacker, we've got background task host spawning as a child of beacon.exe. Okay, so that is not ideal. So what I'm going to show you now is actually running using Covert Toolsmith. So I'm going to tell Covert Toolsmith to run Rubus. I'm just going to give it some arguments. And what you'll see here is we ran Rubus, but there was no child processes created. Now, what has actually happened is, in the background, is Covert Toolsmith has made a request to the web API. It's recovered a .NET binary, which has been bootstrapped with AMSI, ETW. It's it's obfuscated and encrypted, and then it's executed that process inside the beacon. So just skip back for a second. And basically, we've used our own custom CLR harness to inject that inside Beacon's memory and run it all within Beacon, so there's no additional processes created. And afterwards, actually, we unload the CLR to kind of clean it down. So if we take a look at the binary that comes back from Covert Toolsmith, before it is bootstrapped into the reflective DLL that is used in our custom CLR harness, it's dropped to disk temporarily. So I basically dropped to disk on the C2 client, not on the actual endpoint. But I'm just going to recover that so we can take a look, so you can actually see what that binary looks like, just to show you that it's an obfuscated one as well. So I'm just going to pop that up in .peek, and you can see firstly the assembly name is completely obfuscated, and you can see none of the class names and things are visible as well. And that is basically how it works, and that is a nice little approach for executing our own obfuscated, bootstrapped binaries in process without using that kind of fork and run technique that Cobalt Strike uses. So whenever, basically what I want to show is that every time we want to run a tool, we want to build it before we run it, so it's completely fresh every single time. It's completely obfuscated every iteration. If we take this approach, it makes it much harder for blue teams to triage the use of tools and artifacts across the network, and in turn that increases their response time and their investigation with time. In addition to some kind of custom obfuscation that occurs within the pipeline, it also integrates with ConfuserX. So ConfuserX is actually really nice in that it's got an API. So we leverage that API to rename all the resources, add control for obfuscation, add anti-tampering, anti-debugging, that kind of stuff, encrypt all the resources and all the constants to make our binary much harder to analyze, even though we're never touching disk with it and we're just reflectively running it inside memory. So to do this, basically, ConfuserX has got like a small config option that is built inside the Covert Toolsmith web API, and we can just pick and choose which protections we actually want to run, and then Roslyn will basically compile whatever tool, whether that's Rubus or whatever, into the kind of intermediate language. It will then run them through ConfuserX's engine, and then it will take that obfuscated binary and pass it down to the C2 client before it ends up getting delivered to the compromised endpoint. Aside from obfuscation, we might actually want to spend some time kind of protecting our actual individual binaries, because as I mentioned before, there is like a significant R&D investment from red teams, and we don't want all our kind of intellectual property to end up on VirusTotal. So because we have this, if we're using a pipeline, because we've now got this ability to programmatically modify every tool or every artifact that we create, we can also key them. So what I mean by keying is, as a concept, we're basically using like a local or a remote resource to build a decryption key. And so you can find this described better under MITRE ATT&CK's execution guardrails tactic. But basically what we're doing is, let's say, for example, we want to create like a DLL that we're using for persistence, or a DLL that we're using for lateral movement. Using the pipeline, we can do that to actually key it such that that DLL only ever executes on that endpoint, because the decryption key material for running the main contents, the core kind of contents of the DLL, is derived from the environment. So maybe we take the user's username, the domain name, the computer name, and we kind of add all these together into an algorithm. Maybe we take directory listings from program files, that kind of stuff, and we gather all this information, we store it in the kind of Covert Toolsmith backend, so we know what that endpoint looks like, and we use it to build a decryption key for our core kind of functionality. That is basically how it works. So I've got like a little collection tool that runs, and it will firstly recover a bunch of information about the endpoint. It will then submit it to the Covert Toolsmith API, or alternatively, it's actually, with Covert Strike, it's actually also able to use Beacon's built-in data model to gather some information about the endpoint, whether that's usernames, computer names, that kind of stuff. And once we've got this information, when a request for a tool is made, if we also say key this tool, and I say whether that's a loader or whether that's whatever, we'll basically look at the keys from the internal database and then provide an encrypted copy of the tool or the artifact that can only be decrypted based on the environmental keys. And then when the tool runs on the endpoint, or the artifact runs on the endpoint, it will basically, it doesn't have the key built in, but it knows which various different types of properties are used to actually build the key. So it will gather lots of information, and then it will try and brute force its own decryption key before it ends up getting run with assembly.load. So let's look at a little example of this. Okay. So I've got two screens, Covert Strike up on the left, and then a virtual machine with .peak up on the right. So the first thing I'm going to do is I'm just going to tell, using the aggressor script, I'm going to tell it to recover an artifact which has got some built-in shellcode inside it from Covert Toolsmith, and recover an artifact called foobar.exe, and then it will end up getting uploaded to the endpoint inside this temp directory. So on the right hand side, what I've done is just dragged foobar.exe over into .peak, and then if we take a look at it, we can firstly see it's all completely obfuscated. But if we dive into one of the functions, we can see here, this is where the keying is actually occurring. And basically we have this, we have a number of variables that it's taking in, like the machine name, the username, the domain name, external IP addresses, internal IP addresses. And then we've also got this big block of base64, which is actually the encrypted artifact or shellcode or whatever in this case. So if we run the foobar.exe, what you'll see, and I've turned on the debugging just so you can see this better. You can see it basically is trying to whoops, my bad. I was trying to see if I could zoom in. Don't know if that's zooming for everybody, but it at least zooms for me. It's basically trying to brute force its own decryption key based on variables that are derived from the environment. In this case, I made it really simple, and it's just using the user's username. So basically, when the user runs it, they would, if like the blue team captured this exe in this case, they would need to be running it as the same username as the endpoint that we originally generated it for. And that, in this case, basically causes the exe to decrypt when it gets the right username. And we get a beacon pop up because this is basically just using like some injection to spawn Internet Explorer. That's what this artifact does, and that's pretty much how it works. So as I kind of mentioned, the kind of real benefit of using this approach, this kind of operating in code approach, rather than operating with commands, is that we don't actually need to heavily interact with the operating system at all. So if we employ this concept of offensive development, we can achieve everything that we want to do using code. So let's look at like an example problem that we might have. Let's say, for example, we wanted to search. We're searching for passwords in files on the endpoint. Traditionally, you might use something like find string and searching for the pass as a string inside the users folder. Now, this would not look pretty at all from an EDR telemetry perspective. So how do we actually go on and solve this? So using offensive development, what we can do, and this is really cool because you can actually just have the file, the source code file open. So I have a project called like offensive development. I just write things in C# as I'm trying to operate on the endpoint, and then just run them using the CLR harness. So maybe we've just got a source code file that we're working on, and we're just adding stuff to. And every time because it's the tool is compiled and built on every run, we can just have the IDE open and just add lines of code to the source code file and then save it, and then it will automatically run on the endpoint when we want it to. So I'll show you an example of this, how we can actually go about red teaming entirely just from our IDE. Okay, so again, on the right hand side, I've got a source code file, which is literally just printing something to the console. I've got it open in Visual Studio. On the left hand side, I've got Cobalt Strike. So what I'm going to do is I'm going to use Covert Toolsmith to run this offensive dev project on the endpoint. And again, this is actually running from like a Docker container that I'm running inside Visual Studio. So you can see, firstly, it's just printed what we've got in the tool. So it's done the console.write line, and we can see it on the screen. Secondly, what I'm going to do is just make a change to this project. So I'm just going to delete the bits and comments, and then I'm going to add an extra line, console.write line, hello Zifcom. So we're now changing that source code file. So what all this is going to do now is search in the folder users DMC test for text files, and then it will look inside those text files looking for the string password. So we now just save that file and run it again using Covert Toolsmith. And again, this makes a request to the Covert Toolsmith API, which is inside a Docker container. That folder inside Docker is actually shared with my virtual machine in this case, where I've got Visual Studio open with that file, and it will then read the new file, compile the project, and execute it in memory inside that process on the endpoint. And you can see now it's come back saying, we found this file called password.txt, and we can confirm it's working just by kind of looking at the contents of this file. You probably download it. You wouldn't, if we're trying to avoid running commands, you probably wouldn't run shell type, but for the purposes of this demo, we can see it's working. And that basically allows us to do whatever we want completely in code. So not long left now. So in conclusion, I guess what I'm trying to show is that kind of modern EDR-rich environments. Blue teams have got a wealth of telemetry. They can see all the processes that you run. They can see your ETW events. They basically got full visibility of what you're doing on an endpoint. As I mentioned early on, they've got the home field advantage. In order for us to be successful as a red teamer, we need to adapt our post-exploitation tradecraft. So we need to try and blend in better. So blend in with the processes that are loading the CLR. We need to be aware of how they're detecting us so that we can build in evasions. And because there's so many different types of evasions that we might need to consider, if we've got the ability to integrate and leverage DevOps principles into this by using things like a CI/CD pipeline, then that will help us better weaponize and better protect all of our tools. That's finally the talk. Just a couple of shout outs. So firstly to Peter Winter-Smith, who did some really awesome work on building the in-process CLR harness that we use. A couple of ideas I borrowed from Shark Compile, which was written by another MD-Secker from Dave Middlehurst. And then finally, Ryan Cobb did some really cool automation stuff inside Covenant. If you dig into the source code of Covenant, you'll see how it uses Roslyn and some similar principles to what I've kind of used in the pipeline. And that's basically it. I don't know if we've got any questions at all.